Okay, let me show you a little bit of post-tensioning going on here. Don't worry, what's that? Nothing. All right, so this is just wrapping paper, plastic wrap, right? Look, nothing. Terrible. No tension, nothing to hold it. Just a lot of flex, a lot of give. I've got a quantity that we can measure. Watch what happens when I put tension on it, though. When I put a load on it, it's grabbing at the edges. And this load can be determined by, just the weight of it. I think it's 16 fluid ounces, 473 milliliters. Now, I'll release it. And it's on its own, standing there. You see also that it's created a dip. Now, now it's restrained on one side. Crossed here. So now I'll pull it one direction, and now we've got this more tension just in one direction, right? So here's our post-tensioning. All right, so now we do the same thing, and the load is still not transferring over the entire opening. You see it's getting sucked down into the middle of this location of the bowl. But now we'll go all directions. We'll pull that direction. I think I just ripped it. All directions, post-tensioning it in all directions. Okay, now we're getting it tighter. Now, look at the difference. Now it can hold the same weight, but this time, and nothing changed. The material's still the same, but this post-tensioning, I'm trying to get this to stay balanced, if you will. You see now a deflection is practically nil. Same load, but now we've got post-tensioning in all directions. So this is what post-tensioning is about. Now that's just plastic. Imagine what happens, what you can do with this. Is just a very thin layer of plastic, and it was able to hold 16 ounces at the top surface because of post-tensioning. But when you have a failure, it's going to be dramatic. But it takes something. It takes some forces. I just did a puncturing force, right? So let's pretend or imagine this is the cutaway view, a clear view of the bridge, of the structure. It has the concrete with the post-tension cables inside here, longitudinal and transversely. So going both directions. 1, 2, 3 here, and 3 on this side, as drawings show. And then transversely going across. That's the concrete, if you will. Now, without the concrete, this was just the structure itself, the curved shape of the structure. I want to show you that just simply, it doesn't take much at all to create that deflection. Not much pressure at all. Whereas on the other hand, when now you add just a little bit of support, it just is amazingly reinforced. So we grab our 16-ounce container, we put that on there, and it holds no problem. Now we take the same item, 16 ounces, and we get complete. It's almost down to the table. It's a mega difference. Everyone says, well, post-tension cables. I'm not a post-tension cable guy. I totally understand the math of it. I really enjoy them, but the inspection I have a problem with. Not being able to tell, when they're close to failure. Visually inspecting them is impossible inside the concrete. You use other forms of resistance and penetration and, guessing the stress on one end. It's just too much. Until they come up with a better sensor that allows you to monitor it, and it's 100% censoring, and, that you'll know what's going on. That's great. We're just going to use this piece of yarn to demonstrate post-tensioning. And not quite the same length, but when you use the tooling to increase we know you got yarnies, right? Different layers, different strands. So same thing, but when I pull it tight, see, it's coming on the load. It gets tighter, tighter, and tighter. At some point, it won't move anymore. And this is what the kips are about. So now it can't move anymore, but I still want to increase even more tension on it, so whatever the settings are. And I know it's not going to be enough to break the cable, but I want even more tension on it. As I increase that tension now, see how it doesn't stretch now? It doesn't stretch when I'm at the maximum that I choose. So right now it's maximum unless I wanted more tension on it. So as I increase more, you'll see how this works now. So I increased more on this cable. Now I can't, well, right about now I can't increase any more of my finger grips. So it's done. It's at its max. And whatever that, if I can pin my hand there and pin my hand there, we can determine that. Decided to go a different way with that. So here's the cable. I'm pulling it taut because I can visually show it better. So now it's got, so you can visualize the tension that once I put a load on it, it's giving. But once I increase that load, now it won't give. Once I increase it, so that this load will not make this cable contract at all. And if it contracts, the only way this cable can contract is if it slips at my fingers, or if the load starts pulling my hands in. You know, this load here, let's pretend like the load in the middle is so great that it starts pulling my hands in. Once it does that, look what happens. It's pulling my hands in. This changed the whole structure. And I'll show you how this works on this same product. Again, let's do that. We see our failure. Now, let's something work. So here's my little mini model on post-tensioning. So one end is anchored, see, and the other end gets a tooling on it. And the tooling is wedged, if you will, against this outside wall. And this one, this cable, it then starts pulling on it. When it pulls on it, it creates tension inside this cable here. The more tension, well, it can start, as you can see, I'll get to that, but you can see it start pulling on the other end if I increase the tension too much, or ideally, or whatever specs call for, I just pull it enough to get the maximum amount of tension on there per the specs. Sorry, hands got a lot of stuff on it now. I'm working with these chemicals, right? So I can pull too much and cause failure. See how this will even bow the roof, if you will. That's transverse coming across, but that's not what we're referring to. Now I'm going to pin this, show you how this works. I'm going to tack some glue onto it, and give you an idea. Okay, before I do it one more time so you can get an idea of that. So that's the failure. It's almost leveled out. And add the load. You can see the deflection. It's not pushing the ends out. It's not pushing the two ends are in place. Now if I release this cable, it expands outwards. That's where the cable failed. Now watch again. Now I hold the cable in place and I can support the load. This deflection is not reflective of what would have taken place yet. This guy will be this end, and this would be a more reinforced concrete end. So this is just the concrete itself acting as an archway, if you will, this section here. And you can see what's to be gained just by a little bit of a plastic, if you will, by a thin layer. Now let's go from there. So now I think the drawing sort of mimics how the cables, the transverse cables, work like this. See the yellow? I'm not sure of this transverse cable where it's located in here, even in the drawings, but there are cables going down approximately 2 foot, groups of them, every 2 foot 6 inches or so, per their drawings. All I did was take the one container and put it over top of the other. Now it's under tension still, and they're on. Let me put it under tension. It can't go up into the concrete, into this section, because the concrete is impinging it, keeping it located at a certain position. Okay, so I've got it pinned in my right hand, just holding it as a anchor. As you can see, it can take the load. Now that's just a deflection of the plastic. If that was full of concrete, what we're noticing is not, it wouldn't get a compress, but you can see that there's no movement this way or that way as I hold it with my finger as a clamp. When, if this was to break free, this is one transverse cable, for example, it's now totally collapsed. If I could put tension back on it again, it would raise it back up. Let's see if I can show you. As I'm pulling tension on, all I'm doing, see how it raises it back up? Now this would cause cracking more than likely. You can't flex concrete that much. So that's not what took place. It was more, if there were tensioning cables, it was something very, it wasn't trying to lift a bridge back into camber or whatever it may be. That would I think be inviting trouble. All right, so that is just a thin layer again. But this pin, this cable, this transverse cable is holding that load from, it wants to push out on the sides. This cable is embedded in the concrete, so the concrete can't push out on the sides unless, when I release the right finger here, my right side of the image, it will cause a collapse of it. That's not what caused the collapse by itself. Okay, that is the node on top now. Now we got a node, a blister that they put on top of here. Okay, I'm going to show you a little miniature model of something I threw together. This will be number 11. This will be number 10. These are the post. This is the post tension column number 11. It was not supposed to have tension put on it. Per the specs that are online. This should be the canopy. This roof deck is irrelevant at this time, mostly because the failure first started. And this is demonstrating how the failure could have first started at the very top. So these are two columns. There's the roof deck canopy. Here's a post-tension cable, if you can visualize it going through. Well, now you should better visualize it. That's the node, or the what they call the blister. This is sort of a breakaway from it. As I turn this sideways, so these are, it was sort of like a transverse post tensioning in there. No, I'm sorry, that's pre-tensioned. So post is afterwards, pre is before. So this is the one, the canopy. There's a lot of these guys all the way across. The going down. This again would be the node, and this would be the cable that they were, what I have in my hand. This is the cable that was being strengthened, stretched, tightened, tensioned. Okay, so that covers you all. Now, it did have a roughly 90 degree intersection with number 10. And so when you put load on this, when you start shrinking this down, it starts pulling. Number 10 wants to push out. It takes a lot of load onto number 10. And it wants to push down on the lower deck. As you're tightening this, one affects the other. With that said, still, how do you get your failure? This shape of the canopy and the node, so this device is capable of just pulling that cable, and obviously it was able to exceed without failing, the cable without failing was able to exceed the resistance of all the structure down here, including these transverse cables, the column number 11 and number 10. For the most part, I think number 11 failed first, and that it started buckling, as we commonly known as buckling. It started flexing. But before that, I think the deck itself had so much pressure on it. This did create so much pressure that it brought it right to the point of maximum tension before They just shattered, if you will. So imagine this node pushing down. So the cable's getting tighter. And now, come on, baby. I don't want to break up. I've got it just glued down. I don't want to break it. But this whole node, this whole blister, was able to put this whole section into compression, just crushing it. Well, compression pressures. And it kept pulling and pulling. And it was to try to, let me see if I can do this now. I'm going to pull this, hopefully it won't pop my other end of this. So it's going, I'm going to hold this here because it can't move. As this pushed down, see how it pushes the outside walls out? As it did that, the cables became, they were in an arch. These cables are in an arch. At some point, as that thing is straightening out, it went too far, and then at that point just immediately was able to invert, push its way through the deck, immediately, like catastrophically pushes its way through the deck, and transversely, these cables go across. So it only has to pull or fail in one section of this deck. These cables, longitudinal, there were 3 on the side and 3 on the side, although the images I saw might have shown 2 and 2, but let's just... So this is a problem because some of the drawings show 3 longitudinal tendons, some show 2. The actual installation looks like another. Nevertheless, there were none down the middle. So all this at the top, it was concrete, and it's solid. So it tries to act as one piece, if you will. It would be sort of like me telling you to grab a glass bowl and only make the outside layer of the glass bowl move. Well, you can. It's going to move the inside layer too, right? So that's what the solid grouting or solid concrete has an effect of doing. But in this case, it puts so much pressure on it, the cables, these transverse cables, are under tension even more because this guy's pulling down. As I push down from the roof deck, it puts more tension on this guy. At some point, it became so much tension on it that it just pulled this node right through, and at that point, the failure happened. But before that, this guy here, I think, buckled. I think it flexed. So here's a screenshot, and I think that's a flex in number 11. That's the one going down to the bottom of the bridge left. You're looking at the flex somewhere around the upper 1/3. I've slowed the video down twice, and right after this still we're looking at. Take note of how the whole left side fails first. It's got more pressure on it, more speed of failure. Watch now. And we'll see the left flex. Number 11 is flexing. And again, 11 is flexing. So that's the one that failed first. And that makes sense. And that gave it that little bit of time to increase the load out of nowhere. A spontaneous load increase, if you will. Sort of like opening it, pushing on the door, and then somebody unlocks the doorknob. Boom, you go flying across the room. Same thing here. It had so much pressure on it. It just kept increasing the pressure of this number 11, this post tension here. This one that transversely goes down here. So pressing down, and eventually this one flexed, and when it flexed, as opening the door, this just came flying through. This top guy was able to break his way, break the whole deck, and I don't mean literally came through there. I think it pulled up as it caused that failure, and as this collapsed, number 10 and 11 finished pushing this as it collapsed to the ground, drove this out a position where it is on top of the deck, drove it out, and you see it resting on top of the deck, above the deck, with rebar and reinforcement mangled up there. That these two together pushed it outwards, and with the force of hitting the ground. But the failure might have been down at the base here, as this was pulling, but not in a cable. My thinking, it was not in a cable, because if it was in a cable, everything would have reversed. It would have stopped, unless it failed at the same time as the bridge failed, which would be pretty, well, I don't think so. The cable, both ends are intact. If it failed as they were tensioning it, it would just release and things would be put back to normal with some cracks and ability to half hold itself together. So as some people speculate, this cable broke free. Again, I would say not, because it would have released, the whole problem would have came to a stop. I think the failure happened. This guy was cranking up the pressure, and as it did so, it caused the failure. So watch me crank it up. The tension is there. I'm pressing it down, and all of a sudden the cable fails. Things are back to normal. So as you can see, saying it happened inside the cable, saying the cable failed is the wrong approach. It's all about this node flexing this top deck, flexing, I believe, the bottom part here. It could have been somewhere in here. The video, the slow image, if you look at the images of the video, the one guy that did the traffic cam, if you pause it, you can see the right side of the deck is without shutter, without jitter, and the left side is, because it's got an it's accelerated faster than the right side, implying that the left side from here over was at a higher rate of failure, increased speed, more tension, if you will. So there's our rough layout. You can imagine that. Now these guys, these transverse cables, they're going all the way down, 2'6" on center. And it's a bundle of cables, and that stopped this bridge from wanting to go outwards. That helped its tension from wanting to pull out, and so it will not pull out. I'm actually pulling on it. I was kind of hoping this would fail to show you what that would look like, but that glue is holding pretty firm. Nevertheless, as you load the top, you can see it puts tension on there. Eventually it flexed, causing a failure. This guy, I swear, I believe, really got involved, this one, and it's mostly because it's 90 degrees. It's just designed to push out. It's not designed to hold as well as the runner number 2 and 3, which had this so when you start pulling on it, when you start applying pressure here, it transferred the load downwards. I'm sort of getting sidetracked, so let me go ahead and call that video quit. So I'm going to end it with this, that as that was being post-tension, if these guys were in place, that would have helped that upper deck not puncture or pull through or shear through or punch through, however we want to figure out what created it would have resisted a lot more. Now I don't know. I don't have the drawings. I don't know what these are. No one's explaining. But if they had post-tensioning inside there, real cables, which appears there are none, that would have been very significant. Or maybe they failed.